So interference in what sense?
You have two wave packets.
No, I have one wave packet that splits. Right? I have one wave packet, it starts to spread. The part that goes downhill just goes. Oh, yeah, right, and, yes. Okay. So at one time, the uphill part will be able to make high harmonics, may be able to make returning trajectories. And in another delay, only the downhill piece will be able to, and never the twain shall meet, so it's okay. So Ursula Keller's group did an experiment back in whenever this was, 2004, 2005. It's a very hard experiment to do. And it was kind of heroic that they were able to see anything. They were able to basically put in low order harmonics and seed high order harmonics. They were not able to change the delay, which is very hard. Later on, Mark Fracking's group was able to do this where they were able to change the delay. And just to convince you kind of that it works, they put in harmonics up to the 19th harmonic. And then they looked at the signal for the 21st and 23rd harmonic, and they could see that those harmonics were also oscillating as you changed the delay between the two pulses. So this was good evidence that this seeding process was working. So I want to kind of go on now to something else. Another thing, and this is now something where experiments have not been done yet, another strong field process that people study is non-sequential ionization. So non-sequential ionization is a very large correlation effect. Again, a rescattering process where one electron is pulled out by the field, driven back, and then can participate, knock out the second electron, or participate in a process that ends up in double ionization. And in a normal calculation, or experiment where you just looked at tunnel ionization, what you would expect for the yield of, say, helium plus and helium double plus as a function of laser intensity is, well, as you raise the laser intensity, you get more and more helium plus counts. That would start to saturate, right, once you had ionized everybody in the medium. And then you would expect to be on this other curve down here, which is sort of pulling out the second electron by tunneling after the first one has left. But when the experiment is done, that's not what happens. And in fact, as ionization of the first electron becomes more and more probable, you start to get a very non-trivial number of double ionization events. And this double ionization curve is correlated with the single ionization curve because it turns over when you start to have not much single ionization. So this is indicative of a process where the ionization of the first electron participates in the ionization of the second electron. And rescattering explains some, but not all of the features, but this is something that is still studied intensely. I only want to show that this same sort of path selection, quantum path selection, can also work here, so that by changing the delay between the fields, we can determine whether the first electron is able to knock out the second electron or not. So these are hard calculations to do, and you want to do a whole lot of them because you want to look at delay and all these things. So you knock down the number of dimensions. So we did this as an aligned electron model. That's where you picture two electrons that move on a line. So that gives you a 2D space that you have to do the calculation on, right? One coordinate for each electron. And when you do those calculations, you can reproduce something that looks like this non-sequential double ionization spectrum. So here you see, as a function of IR intensity, you see the single ionization coming up and saturating, the non-sequential double ionization coming up and also turning over when this saturates. And this little piece where it continues, that's the sequential ionization. That's just the pulling the second electron out by tunneling after the first one is already. So I have a model calculation that reproduces this. So now I can go ahead and put in this sort of funny pulse that has both an attosecond pulse trend and an IR. So this is kind of a movie of what you get. It's a 2D movie. And so when stuff moves along one or the other axis, that is single ionization, because that corresponds to one electron staying at small coordinate and the other moving at large. And the stuff that moves off in these directions, that's double ionization, because both coordinates are getting large. And so you can see that as you do the calculation, you can get a non-trivial amount of double ionization to look at, and then you can go analyze that. And so here's what you get, and it's kind of the same story as with the harmonics. So now the helium plus here, look at this, it's very, very much the same at all intensities. Why is that? That's because it's only the IR intensity that's changing. The attosecond pulse intensity is not changing. So it makes the same amount of ionization, no matter what the IR pulse is, right? So I get a very constant amount of helium plus signal up until the IR intensity gets big enough to start making a big contribution from tunneling on its own. And I have this non-sequential double ionization signal. And if I look at that signal, the yield of helium double plus, these two, the green and the red curves, that's for two different delays between the attosecond pulse train and the IR pulse. And so by changing the delay, I can change how much double ionization I get by about an order of magnitude. So I really am also controlling this double ionization process. I'm allowing the electrons to interact or not. It's interesting because this is sort of a technicality, but in the yellow part here, the returning electron has enough energy on its own to knock out the second electron. But there's a lot of double ionization here where the first electron doesn't really bring back enough energy all on its own to ionize, just to knock out the second electron. But it participates in a process where they both get excited for a little while and then go on out. And this is just to show you, I showed you a plot like this the other day. This is looking at the space-time trajectories from the full quantum calculation for two different delays between the attosecond pulse train and the IR pulse. And you see that it's very different. Here is a delay where there's essentially no returns of the first electron, so there's no double ionization. And here's a delay where there's a lot of returns. So I mean, you really are just controlling the population of these space-time paths with this. Another thing that's very interesting, we talked this morning, Paul talked about the CEP phase, the carrier envelope phase of the IR pulse, and this is something that's been measured by various nonlinear processes over the years. It's not possible to measure the CEP phase in a linear process that I'm aware of. This is, pretty sure I'm right about that. So this is kind of a problem if you were to say, I have an attosecond pulse train, and I know I have an attosecond pulse, and I know that my pulses are just a few cycles, maybe 1.5 cycles. So then I could naturally ask the question, what is the CEP phase of my attosecond pulse? Well, now we have a problem because the attosecond pulse spectrum is high, right? The frequency is high. So it basically just does single ionization. So I'm not really able to see the CEP just from looking at ionization events caused by the attosecond pulse train. And so if I think of my attosecond pulse train as being made out of synthesizing a bunch of harmonics together, the qth harmonic, q times omega 1, where that's the driving frequency. There's some phase, this is the so-called attochirp phase. And then I'd like to know this CEP phase, but how could I find it out? And it really is different, right? I mean, just like Paul showed, depending on if the phase is 0 or pi over 2, these are two different electric fields. Right? So I might like to know that. And this effect of changing the delay, and it turns out that if I set the delay at a point where I get a lot of non-sequential double ionization, and then I change the CEP phase, I can modulate the amount of double ionization that I get by a pretty healthy amount, factors of 2, 3, 4. So this is a process where I can measure the CEP phase. And I said, and I wasn't lying, that you need some nonlinearity to measure the CEP phase. The nonlinearity in this case is provided by the electron-electron interaction, right? The one electron coming back and interacting with the second one. And this allows this phase to be the principal measure, which I think is kind of interesting. I don't know why this is repeated, I apologize. There's nothing to do but keep pushing buttons. Okay. Let's go back and try and look at rescattering in a little more detail. So what about this single ionization that the attosecond pulse causes? Can we probe the single ionization and rescattering event with a train of pulses? And so in collaboration with Johan Moritzen and then Bouillet, about 10 years ago, we did an experiment that was kind of a quantum stroboscope as a way of looking at the electron wave packet that gets made by ionization. And so here was sort of the toolkit for doing that. We needed a train of identical attosecond pulses because in a stroboscope, you want to look at the same event over and over and over again at a set delay, right? And so in our case, we're going to make the same wave packet again and again and again. So we need to make sure that the wave packets that are made by the attosecond pulses are actually all truly identical. We need a train of identical pulses. We need to synchronize those to the guiding infrared field. And there was a velocity map imaging spectrometer to look at the momentum distribution of the electrons that come out. Well, if you look at the pulses in an attosecond pulse train, they're actually not all alike. Every other one is flipped with respect to each other. In other words, if you use a comb of odd harmonics to make a bunch of attosecond pulses, they will not be identical. Every other one will have a pi phase flip between them. So if you look at this in detail, this one, the thing points up, and there it points down, and here it points up. Right? So those are not going to make identical wave packets. So what they were able to do in Lund was to make an attosecond pulse train where instead of a pulse every half cycle, you have a pulse every full cycle. You do that by mixing two colors in the driving field. The fundamental at 800 nanometers, the doubled at 400 nanometers. And this, if you do things right, and you can get phase locking so that you will get a sequence of identical pulses that are now spaced one period apart. Doesn't always have to come out like this, but you can find conditions where it does. And so, basically what they did in Lund then was once they had the attosecond pulse train with identical pulses spaced at a cycle, they just redid the standard streaking experiment, right? Just like Paul was talking about. Depending on when the attosecond pulse comes and launches the wave packet into the continuum, the wave packet will be sheared. It will have momentum either added or subtracted to it. So it will be pushed either up in momentum space or pulled down in momentum space. And so in this experiment, what we would expect is we have a whole bunch of identical pulses that's going to make a whole bunch of identical electron wave packets, and we're going to do nothing to them, or push them up, or pull them down, if it works. And this is actually the data from the experiment, and it does actually work. So here is a delay where no momentum is added to the momentum distribution, and it's symmetric around 0. Here it is pushed up, here it is pulled down. So you can actually put these together and you can make a movie of the momentum distribution of the ionizing electron being pulled up, pushed down, pulled up, pushed down. Right? Now, and so that just sort of shows that it works. For instance, it shows we really do have a train of identical pulses. Right? you choose the conditions wrong, it doesn't look that nice because your pulses are not so nice. What's an application of that? An application of that is, let's look at rescattering. So again, do the same sort of thing. So we have, we can choose to have our attosecond pulses come at a time when the electric field due to the IR is temporarily 0. So I'm launching wave packets at a time when the electric field is 0. Or I could launch the wave packet at a time when the electric field is big, or 0, or big the other way. Right? This corresponds to maximum vector potential, 0 vector potential, maximum 0. So actually, this guy gets kicked a lot, this guy gets kicked not at all, this guy gets kicked a lot, that guy gets kicked not at all. That's kind of a homework assignment. Prove yourself to that. But the equation was on one of Paul's slides this morning. And so what you see, what we wanted to see here was, if we turned up the intensity of the IR field, could we guide the wave packet back so that it would actually rescatter? In other words, could we make wave packets, have them go out, and actually choose a phase of the field such that we could push it back and see it get rescattered off the potential? And you have to see here that these momentum distributions, which are again made in helium, but now at a higher intensity, where the IR intensity is high enough to actually redirect some of the electrons, we actually get a non-trivial amount of backscattering in the down direction and then the up direction if we choose the phase of the field as such that we can add or subtract a lot of momentum from the electrons. And this is the experiment that Johan Morrison did. This is sort of a match between theory and experiment, so we were kind of happy with that. So we think in the future this could really be used to do this sort of selective scattering where we make wave packets and guide them back. And you could think of doing three-dimensional, what did you call your pulses? I mean, they were magical, amazing.
Oh, crazy light pulses.
Crazy light,
yeah,
crazy light
This is
pulses.
an experimental term.
Yeah, we could use the crazy light pulses. Let me call them magical. And now you won't be a drink. Use a magical or crazy light pulse, right, to sort of guide the electron back to somewhere and see what we were doing. And this is kind of the key point is, because I am controlling the ionization and all of the wave packets that I'm making are precisely the same, then whatever happens from one wave packet and one rescattering event, it's just going to add up coherently. And I'm going to see this nice n-squared enhancement in the signal. And that's why it's a quantum stroboscope and not a regular stroboscope, right? It's the bunching of the signal that you get from repeated interference of the same thing. So this is the last thing I want to talk about because it sets up my talk on Friday. This is another experiment that was done in Lund in about 10 years ago. No, less than that, maybe 8 years ago. But they did an experiment, again, using an attosecond pulse train and an IR pulse that were precisely synchronized to control the amount of ionization that you could get, again, in helium. And so here's how this worked. So here's the paper. So this is a spectrum. This is energy over here. This is the first thing that I'm going to show you is the same electric fields applied to two different atoms. Okay? So first to argon atoms. So they have an ionization potential that's a little bit above 15 volts. And then the helium atom, which has an ionization potential a little bit below 25 electron volts. Now the attosecond pulses that were used in this experiment, and again, the intensities were adjusted such that the attosecond pulse was driving the ionization. Okay? The IR pulse is just moving the electron around once it gets excited. The attosecond, the harmonics in the train were 17, 15, 13, 11, mostly below threshold in helium, all above threshold in argon. So this is an experiment where we either make wave packets above threshold in argon or below threshold in helium and look at the difference between those two things. Here's one of the pulses in the attosecond pulse train, about 370 attoseconds long by measurement. this is a measurement of the velocity map image, so the momentum image of the electrons that are ionized when there is no infrared field present. And so what you see for this is for argon, you have 1, 2, 3, 4 rings there, because there are 1, 2, 3, 4 harmonics, and so you eject electrons with the 4 different possible energies. You're not bothered that these fringes are not equally spaced, right? Because this is velocity, not energy. Energy is velocity squared, right? Okay. So the spacing between the fringes is the square root of energy. So for argon, I have 4 fringes. For helium, I have just 1 fringe, because only the 17th harmonic can ionize electrons. Now turn on the infrared field. Okay. So now look at the ionization signal as a function of delay between the IR field and the attosecond pulse stream. The first thing to notice is the flat line here. The flat red line is the data in argon. And basically in argon, the amount of ionization that is made is independent of delay. Because you're basically just putting wave packets into the continuum. Now, granted, the IR field is adding or subtracting some momentum, but that doesn't change the total signal, right? It doesn't change the total ionization signal, right? So what's along here is basically the population of the wave packet that gets made, and that is not dependent on delay. But in helium, where most of the wave packet is below threshold, now we get about a 30% modulation in the ionization signal, which had not been done up to then. So this is sort of something that builds on the idea of streaking, but instead of just changing the momentum distribution of the emitted electrons, it actually modulates whether the electron gets out or not. And these are, again, velocity map images of what's going on. Now you can see for 2 different delays, as I promised you, for argon, similarly, if you integrate over the blue disks, they give you the same number. That's the total ionization signal. But you can see that the momentum map is different. By the way, right, this is an experiment done with odd harmonics, which means there's a pulse every half cycle, which means that we're ejecting wave packets both up and down, which means that this momentum distribution, instead of getting pushed in just one direction, right, it gets stretched, right, because there are wave packets that are made both downhill and uphill. Or there's a wave packet made one time and then a half a cycle later, not a full cycle later. So the ones that are, if you make a wave packet at one time and it gets momentum added to it, the wave packet that's made a half a cycle later will get momentum subtracted from it. So it just gets stretched. And so it looks like it should. The helium velocity image map for the 2 different delays look very different, and they are very narrow along the axis. And this is, again, because the IR field is assisting with the ionization process. And so we come back to this, and then we say, well, what is the problem that we're actually studying in helium? And it's actually a very interesting problem, because the intensity is kind of low. Oh, it was on the previous slide. But the intensity is just like 1.3 times 10 to the 13. It's a very low intensity as strong field physics goes. But here's the thing. If you look at this distorted potential that we've been drawing for the past 2 days, and you ask yourself, how far is this saddle point pulled down from 0? It's actually, this is a number that scales very, very slowly with the field. The epsilon out here is the field amplitude. So it actually scales like the quarter power of the intensity. This means that already at 10 to the 13, this barrier in helium is pulled down by 7 electron volts, which means that essentially all of the excited states of helium are above this barrier. That to me is a strong field. I don't know about you, but I think that's a good definition for being in a strong field. If the electric field is able to pull the barrier down below the state I'm trying to live in, right? It's like taking the bottom out of the bucket that I'm in. So And yet, a field of 1.3 times 10 to the 13 does nothing to an electron that's in the ground state of helium, right? So this is really, to me at least, a very interesting kind of strong field physics to do, where you take an electron and you just inject it into this strong field at a time of your choosing. And also a place up or down here of your choosing. You could chirp it, as we talked about. You could do all sorts of things. So they had a 10 femtosecond attosecond pulse train, 35 femtosecond probe. They created one or more electron wave packets in this strong field. All the wave packets are the same when they're born. They're all born in the center of the potential, where the electric field is not having very much effect at all. So you make a bunch of wave packets that are essentially identical to what you would make if the IR field wasn't there. But then the IR field has quite a strong influence on the wave packets after they get excited, but not before, and actually not during. You ask me, how do I know not during? Well, if I have just a single attosecond pulse, okay, and I look at how much excitation I get, it's independent of delay. So, and also you can make a movie and convince yourself that you're making the same wave packet every time. What happens to the wave packet after you make it, completely dependent on the phase of the IR field that you make it. So you have, again, this real control knob, which for doing strong field physics, I think is really interesting. So that's just the same thing. And you get very, very interesting, very sensitive dependencies on here is the delay, and here is the amount of excitation that you get out of the ground state. And if you ask the question, why was the ionization modulated? Why was the helium ionization modulated? The answer is because the absorption of the XUV field is modulated. Okay? That's the bottom line thing, which unfortunately I cannot prove to you tonight because I have to give you a lecture on transient absorption and what is that, and the way that you can calculate the absorption. But this is what it turns out to be. So the amount of total absorption that you get is what's shown here as a function of delay. And you see that if you pick an intensity like the green line is 10 to the 13, you get a nice modulation, which can easily be 30%, which peaks at the quarter cycle of the field. In other words, it peaks for making the wave packet when the electric field is large. But if I change the intensity just a little bit, lower it down, I actually get the total absorption to peak at a time when the field is zero. So these sorts of calculations, which come from just calculating what's happening with the electrons, to understand those, we said, well, we have to understand how is it that the light is being absorbed. What's going on with the absorption of the light? What is changing when I have the IR field there? And why is it so sensitive to the delay of the IR field? And that launched us off into a set of transient absorption calculations, which will be the lecture on Friday. So I'll stop there.
Thanks, Ken. Great. Question? Yeah.
In your analysis of the helium double ionization, you were looking for a method to measure the carrier load phase.
Yeah.
And you
Actually,
said,
I was just interested that it varied at all.
right. Well,
Nobody asked me
you
to
said,
measure the
you said,
phase.
you said correctly that
Yeah.
The first order process you can't measure.
Can't measure.
You need a non-linear process.
Yes.
But didn't you have an IR field in there with the attosecond pulse train or not?
I did.
So I would say it's not the non-linearity between the attosecond pulse train and electron correlation, but between the attosecond pulse train and the IR.
Right, and so I would say that too, but I turned out to be wrong. And so, or I think I'm wrong, and the point is that if you were right, then this amount of single ionization that you get should be sensitive to the carrier envelope phase, and it is not.